One example I brought you here is on courtesy of BOSCH. They used network coding for their CAN bus. I don't know if you know what this is. This is the traffic network inside a car. It's very simple, and what they have done, I will try to show you. Their problem is, on the CAN bus, they have different devices, and you don't know whether this device is connected to the CAN bus legally, or if he tries to come in to inject packets and to hijack the car. So there were some times when they just broke off the window, the mirror, and there was the CAN bus that put something on top and could start the car, right? It was stupid. So in order to keep the entities in the car secret, they need a key. So they need to make a key exchange. And the key exchange, if you're already on the CAN bus, you can hear them, right? And what they are using, which is something that we did not talk about in the analog one, when Alice and Bob are sending to the relay, what happens on the relay is a superposition of the signal. But the relay does not know what really happens. He just got a superposition. He will do something with it and send it out. But he doesn't know really what the message was. In the digital domain, we send packet A, packet B, and there the secret is revealed. And what they're doing is they're looking a little bit into the analog one where they had some security features. Now, if you look into the basic idea, you have the CAN bus here, as you can see, and Alice and Bob, and they want to exchange a key. So what they say is, if Alice sends the key and Bob at the same time, they just have to say, let's send at the same time. They will send at the same time. Everybody who listens it will get a superposition, will not understand the key, but Alice will receive Bob's and its own coded signal, look into that and say, okay, it's a superposition, but I have one of the keys. I can use this to clean up the mess. That is nice. The only problem what they had on the CAN bus is it does not act like a broadcast medium. So if Alice is sending a 0 and Bob is 0, it's a 0 on the bus. If Alice sends a 0 and Bob a 1, it's a 0. If Alice sends a 1, Bob is 0, it's still a 0. So it's not behaving like we had before, right? Now it's not 50-50. You see that 75% is a 0 and only 25% is a 1. And what can you do here? If it's a 1, you don't even, you say, okay, here can, if you are Alice and you see a 1, you say, okay. But if you are Alice and it's a 0, yeah, what was it, right? Can be anything, right? No, I mean, if you're Alice, it's not true. If you're Alice, you know it's a 0, then you know Bob sent a 0. But if you send a 0 and it's a 0, it could be also the other one. You don't know what the other one sent, right? That is the problem. And what they came up, and this I like very much, is they overcome this by just saying, okay, instead of using 0 and 1s, we are just replacing a 0 by a 0, 1 and a 1 by a 1, 0. They use some padding, okay? And the same mapping happens also at Bob. And then if you then overlay it, right, suddenly you get new code words, right? So 1, 0 or 1, 0 means now both users have transmitted identical bits. 0, 0, both users have transmitted different bits. So from the attacker, you cannot see anything, but they know what happens. Once they receive it, this means we have transmitted the identical bits, and this means we have transmitted the same bits, right? So now we can get out the sequence and get out the key for both sides. I think this is quite interesting. So if you have this key exchange, there are other things that they can do with it. I will not go into detail. You have the slides for yourself. But for the implementation aspects, for example, if you send 5 equal bits in a frame, a stuff bit has to be introduced. So if you always send the same one, they understand, okay, they're nulling themselves out. And nulling yourself out is not good. Why? You're losing the rate, the tick of the signal. So it's good to send in once a time a stuff bit just to avoid the long 0 sequences, right? Then there are other stuff that this is showing you the introducing of the bits. You can look into this. And they also would like to have a CRC per to understand whether the payload was correct. So if you make a CRC on your payload and a CRC on your payload, how does it work here? So if you map two payloads, can this be a good payload over here, right? Because the combination in this case normally does not result in a valuable CRC bit. Now, what you do there is you make a CRC over A and B at the same time, and then you have a new CRC bit that will help you to understand whether the packet was correct or not. Because this is for the key very important. Now, just to explain you how the performance is, if you have n bits on Ella's side and Bob also, and we assume the keys have the same length, then you see that the extended bit string, because we are mapping 1 bit to 2 bits, is twice as big, right? So the superimposed bit string is twice as much as before. There's some inefficiency in that, right? But you have the shared secret inside of that, and that is the one that they really would like to have. It doesn't matter so much because the key, once you exchange it, the rest of the communication is used by this key. You don't have to do this all the time. That just happens for the key, not for the later payload. Okay, then the question is what happens now if Alice and Bob are communicating and you have one malicious attacker on that? What you will see here is when Alice and Bob are transmitting certain bits, what they really observe, right? If you're sending 0101, then the Eve will see 01, and Eve has full knowledge of bits transmitted by Alice and Bob, but bits will be discarded anyway, this one, right? In this case, he cannot see what happens. Eve is not able to tell who has transmitted 01 and who has transmitted 10. Here's the secret, right? And here, Eve has full knowledge, as here, as bits transmitted by Alice and Bob, but bits will be discarded anyway. This is interesting to understand where the secret comes from. It's in this phase where we null out the signal for Eve, right? And then by the superimposition, you have here Alice, Bob, and Eve, and what happens really on the CAN bus. And with Eve is introducing something. So Alice and Bob want to transmit 00, and Eve is just injecting some evil stuff here, right? So therefore, if it's only 1, right, then there's no impact. But if you have certain other attacks, it requires a better look. So what I really like here is the engineering approach. Just take the idea, superposition of signals, get a secret out of it, understanding that your own system does not have the same properties, align it to the new environment, and go through it step by step where it really could have an impact or not, and where the attacker can have something later on. And this is then the result that in the end they can achieve a full security exchange of the key, which is really the idea behind that. So there are some other stuff that you can have a look at, right? There's some demonstrators that they build up with Eve as an introduce some traffic there, but you could see that the keys are always intact and the communication is always secure. I've seen that quite interesting. Okay, so this was an example by BOSCH.